Hello linear algebra students. This video lesson is the second part of a lesson on eigenspaces. Now eigenvalues and eigenspaces can also involve non-real values, so imaginary numbers. Find the eigenvalues and corresponding eigenspaces for the matrix below. We set up our characteristic equation like normal. So we want 0 to be equal to the determinant of this matrix with r removed from the main diagonal. So we'll have negative r in the 1, 1 position and 2 minus r in the 2, 2 position, and the other two entries do not change. Calculating this determinant, we get negative r times 2 minus r, and then minus the product of the other two entries, so minus negative 2. This gives us r squared minus 2r plus 2 as our characteristic polynomial. This polynomial does not factor, so we use the quadratic formula. So the opposite of b will be 2 plus or minus the square root of b squared, which is 4, minus 4ac, that'll be minus 8, all over 2a, which will be 2. This gives us 2 plus or minus radical negative 4, all over 2. The radical of negative 4 is 2i, and then dividing everything by 2, we get 1 plus or minus I. Now these two roots are called complex conjugates of each other. And in general, a plus bi and a minus bi, where b is positive, are called complex conjugates. So we continue with our process. We begin with one of these two eigenvalues. Let's go with 1 plus I. We remove this eigenvalue from the main diagonal of A, multiply it by an eigenvector x, and set it equal to the 0 vector, and create an augmented matrix. Now the coefficient matrix will be basically what you're seeing right here, but with r being 1 plus I. So here's our coefficient matrix, and our augmented matrix would have the 0 vector on the right. Okay, simplifying, our augmented matrix becomes this. And the Desmos matrix calculator does not row reduce matrices that involve imaginary numbers. Now you can try to find an online calculator that will, but I will do this one by hand. So my goal is to make this position here a 1, so I'm going to divide the top row by negative 1 minus I. That gets me to this matrix. Now we want to do a little bit of review of what it means to divide by a non-real number. So recall that if you have some sort of real number divided by a non-real number of the form a plus bi, you can make the denominator real by multiplying this by the conjugate of a plus bi, which is a minus bi, over itself. We'll leave the numerator factored, but I will distribute or FOIL the denominator. We're going to get a squared minus abi plus abi, so the abis will cancel, and then minus b squared I squared, but I squared is negative 1. So we wind up getting a squared plus b squared, which will be a real number. This will allow us to put our fraction that had a imaginary number in the denominator into standard form where the imaginary numbers are in the numerator. So we do want to simplify this expression right here by multiplying top and bottom of it by the complex conjugate of the denominator, which will be negative 1 plus I. So our augmented matrix becomes negative 1 plus I all over, and when I FOIL the denominator, I just get a squared plus b squared. So it'll be negative 1 squared plus negative 1 squared, which is 1 plus 1, which is 2. Now that I've done this, my goal becomes to turn this entry here into a 0. So I will multiply the top row by 2 and add that to the bottom row. So 2 times 1 is 2, add to negative 2 will make the 0 that I want. And conveniently, we have negative 1 plus I over 2 times 2. So that will just become negative 1 plus I, and then add that to 1 minus I. And everything cancels, and we get 0 again. And then, of course, we'll get a 0 in the last position. Now, this is not surprising because we expected a singular matrix, so we expected a row of zeros down here if we did everything correctly. So now we are in reduced row echelon form. Let's identify our free variables. We have a pivot position right here, and one free variable, which is y. So the first row gives us that x plus negative 1 plus I over 2 y has to be 0. So in other words, that x has to be equal to the negative of negative 1 plus I over 2 y, which we could distribute that negative through the numerator and say 1 minus I over 2 y. And then y is free. So our eigenspace will be the span of a vector of the form. The first component will be 1 minus I halves, and the second component will be 1. Now, if you don't want the fraction in there, you can go ahead and multiply this basis vector by any non-zero number. Let's go ahead and double it. And so we'll say our basis vector is now 1 minus I, 2. Now I'm going to repeat all of this for the second complex eigenvalue, r equals 1 minus I. So we construct our augmented matrix. Now let's simplify the entries, getting this matrix here. You're going to notice as we do this a lot of parallels with the work we did over here with 1 plus I. The entries we're seeing over here, the imaginary parts are complex conjugates of each other. So there's i's in these two components along the main diagonal, and over here we have the same main diagonal except they're complex conjugates, where the imaginary part is changed sign. Now to achieve reduced row echelon form, I'm going to make the 1, 1 position a positive 1 by dividing the top row by negative 1 plus I. And then I will simplify this term right by multiplying numerator and denominator by the conjugate of the denominator. Will take me to this matrix. Now I'll continue with my row reduction, multiply the top row by 2 and add that to the bottom row. That will zero out the bottom row. Again, notice the parallels between this stage and this stage. They're identical, except that the only position we have a complex number, which is right here in this numerator, we have the complex conjugate of it in this position. So converting the first row to an equation, we get the following, solving for x and establishing the fact that y is free. So the first coordinate has to be 1 plus I halves times y, and the second coordinate is free. Therefore, we get an eigenspace that is the span of this non-zero eigenvector. Of course, we can double the two components and rewrite this as the span of the eigenvector 1 plus I first component to second component. So again, notice the parallel. The eigenvector that we have over here for r equals 1 plus I, and here's an eigenvector corresponding to 1 minus I, and notice that wherever there's an imaginary number in the first component, we have the same vector except the complex conjugate in that component. And wherever there was a real number, we have no change. This will always be the case. Notice down here, if you have eigenvalues r1 and r2 and they're non-real complex conjugates, then corresponding eigenvectors v1 and v2 can be found, and they will also be complex conjugates. Because of this, all you really have to do is the work you see right here, and once you have this eigenvector that forms a basis for this eigenspace, you can simply do the complex conjugate of it, and this vector over here will be the result of doing that, and it will serve as a basis vector for the eigenspace corresponding to the complex conjugate eigenvalue. And this will be true no matter how large of a matrix A was, 3 by 3, 4 by 4. You will notice that all of your non-real eigenvalues will come in complex conjugate pairs. Okay, let's go to the next slide. Find the eigenvalues for each matrix below. Now I want you to notice that this is a symmetric matrix. The main diagonal could be whatever numbers, but the entries off the main diagonal you see a symmetry. So in this case, these two numbers have to be the same, and this would be a symmetric matrix. Now setting up our characteristic equation, we get 0 equals the determinant of 2 minus r, 3 minus r is the main diagonal, and 1, 1 stay the same. This gives us 2 minus r times 3 minus r minus 1 as the characteristic polynomial, which we will expand, giving us r squared minus 5r plus 6, but then do the minus 1, so we'll have plus 5. This polynomial does not factor, but we can use the quadratic formula. R is equal to the opposite of b, which will be 5, plus or minus the square root of b squared is 25, minus 4ac, that'll be minus 20, all over 2a, which will be 2. So this gives us r is equal to 5 plus or minus radical 5 all over 2. Now I want you to notice that the two eigenvalues here are real. That's because the discriminant, the inside of the radical, wound up being a positive number. So we did not need imaginary numbers here. Now the two eigenvalues are irrational, but they are still real. Okay, let's look at the 3 by 3 case here. Now, the main diagonal could be whatever, but notice the symmetry. The zeros are the same, the 2's are the same, and the zeros are the same. So this is a symmetric matrix. Let's go ahead and find the eigenvalues by setting up the characteristic equation. 0 equals the determinant. Remove r from the main diagonal, and all the other entries stay the same. Now to find this determinant, we're going to use cofactor expansion along either the middle row or the middle column, because there's two zeros in both. Let's go ahead and just do cofactor expansion along the middle row. The signs of the middle row will be negative, positive, negative, using the matrix of signs. So we only really need to do the targeting of the 2, 2 position. So this determinant will be positive 1 minus r times the 2 by 2 determinant not currently crossed out, which will be negative 2 minus r times itself, so squared, and then minus, and then 2 times 2 is 4. Okay, we can continue to factor this by hand. 1 minus r, we'll leave that factored out, but inside these brackets we'll simplify. Squaring negative 2 minus r, we wind up getting r squared plus 4r plus 4, and then we have this minus 4 still. So the constants cancel, which will mean we can continue to factor, because we'll just have r squared plus 4r left. And I can factor out an r, which I'll write in the very front, times 1 minus r times r plus 4. And then we can see what the 3 eigenvalues are here. The first eigenvalue will be 0, then 1, then negative 4, corresponding to the same order that I wrote the factors. But again, I want you to observe that all of these are real. Now reading down here, it turns out that the eigenvalues of a symmetric matrix that has real entries are going to be real themselves. That will always be the case. Okay, let's go to the next page. Find the eigenvalues for each matrix below. Now this is a 2 by 2 matrix, but notice it has a 0 off the main diagonal. So technically this is a lower triangular matrix. Remember, to be a lower triangular matrix, you must have zeros above the main diagonal, everywhere above the main diagonal, and the main diagonal and below the main diagonal can be whatever. Setting up our characteristic equation, remove r from the main diagonal, leave the other entries the same, calculate the determinant. So we get 3 minus r times 4 minus r, and then minus 0. So I don't need to bother writing that. And we already have, just like that, a factored characteristic polynomial. So the 2 eigenvalues are just going to be 3 and 4. Also notice that the matrix, after I remove r from the main diagonal, will still be lower triangular. And if you recall from our discussion earlier about triangular matrices, it always turns out that the determinant of a triangular matrix is simply the product of the entries on the main diagonal, which is exactly what we get right here. And when you solve this characteristic equation, you wind up getting eigenvalues that are exactly the entries that are on the main diagonal. Let's look at matrix B. Notice that this matrix is upper triangular. To be an upper triangular matrix, it's the entries below the main diagonal that must all be 0. The main diagonal and above the main diagonal can be whatever. Also recall that if a matrix is both lower and upper triangular, we call that a diagonal matrix, which means that off the main diagonal has to be 0, and on the main diagonal can be whatever. Setting up the characteristic equation, we get 0 must be equal to the determinant. Now remove r from the main diagonal, leave all other entries the same. Notice the result is still upper triangular. And we learned that the determinant of an upper or lower or any triangular matrix is simply the product of the entries on the main diagonal. So this determinant will be the product of 1 minus r, negative 2 minus r, and 2 minus r. And when you set these factors equal to 0, solve for r, you will simply get the eigenvalues are the entries on the main diagonal. You could confirm this with doing cofactor expansion along the first row. That 1 minus r is in a positive position, and when you cross out its row and column, you get 1 minus r times the determinant of that 2 by 2, which is just going to be the product of the main diagonal again. But notice that the eigenvalues are the entries on the main diagonal. So if you're working with a square matrix that is upper or lower triangular, or even diagonal matrix, then you can spare yourself a lot of work. The eigenvalues will simply be the entries on the main diagonal, which is summarized in this comment down here below. Okay, let's move on to the next page. Now the trace of a square matrix is the sum of the entries on the main diagonal. Find the trace, capital T, and determinant, capital D, of the general matrix below. And this is a 2 by 2 general matrix. So let's do that first. Capital T will stand for the trace. The trace is the sum of the entries on the main diagonal, so it's just A plus D. And the determinant, we'll use our 2 by 2 crisscross method, A times D, and then minus B times C. Now let's read here. Then find the characteristic polynomial and express it in terms of T and D. We'll set up the characteristic equation here, which is 0 must be equal to the determinant. Remove r from the main diagonal, leave the other two entries the same. So we get 0 must be equal to a minus r times d minus r, and then minus b times c. Go ahead and FOIL this expression. We have 0 is equal to, this will give us r squared minus ar minus dr plus ad. And then we have the minus bc still. Now these two middle terms, I'm going to factor the r out and the negative. That gives me r squared minus parentheses a plus d, end parentheses, times r, So I factor the negative to the front and the r to the right, not that it matters, plus, and then we have this AD minus BC constant over here. But notice what you get here, that this is the trace and this is the determinant. So we can write our characteristic polynomial as r squared minus the trace times r plus the determinant. Okay, continuing to read up here, then find the eigenvalues in terms of t and d. So the eigenvalues will be the two solutions to this equation. We will use the quadratic formula to find them. R will be equal to, we'll do the opposite of the coefficient of r, which is going to be just capital T, the trace, plus or minus the square root of, and then we square negative t, so we get t squared, minus 4ac. So minus 4 times 1 times the determinant will be minus 4 times the determinant. And this is all over 2a, so all over twice the leading coefficient, which is just 2. And these are our two eigenvalues in terms of trace and determinant. And finally, let's do the last step. Then find the product and sum of the eigenvalues in terms of t and d. Let's do the sum first. So the two eigenvalues we will add together, r1 plus r2. And the two eigenvalues come from here, where one of the eigenvalues has the plus as the operation, and the other eigenvalue will have the minus as the operation. So here's the first eigenvalue, and we'll add to that the second eigenvalue. Now these have a common denominator already, so I can just add the two numerators. And when I do that, the t's will add to become 2t, but the two radicals will cancel each other. And all of this will be over the common denominator of 2. So this will boil down to 2t over 2, which we just get t, which is the trace. So this simplifies nicely. And it's remarkable that the sum of the eigenvalues equals the trace, which was the sum of the entries on the main diagonal. Now let's multiply the two eigenvalues, r1 times r2, find their product. All right, the two numerators are conjugates of each other. We have an a minus b and an a plus b. And when you FOIL that, you should just get the difference of squares. So we'll get t squared minus t times the radical plus t times the radical, which will cancel, but then minus the square of this radical. So the FOIL process should yield t squared minus, and then squaring the radical just gives us t squared minus 4d. The radical goes away. And all of this is over, and multiply 2 and 2, and we get 4. Now distribute this subtraction. It gives us t squared minus t squared plus 4 times the determinant, all over 4. So this gives us 4d over 4, and we simply get the determinant. So this is rather remarkable too, that the product of the eigenvalues will be equal to the determinant of this 2 by 2 matrix. Now what's fascinating is that these findings generalize. Reading here, for a square matrix, it doesn't matter how large it is. The trace is the sum of the eigenvalues, and the determinant is the product of the eigenvalues. We've proven it for the 2 by 2 case, but moving forward, these relationships will be true for any square matrix. Okay, let's go to the next page. Now use technology to find the eigenvalues and corresponding eigenspaces for the matrices below. There are many different eigenvalue eigenvector calculators that you can find online. If you go to Google and do a search and type in eigenvalue calculator, one of the first ones that pops up will be this Wolfram Alpha eigenvalue calculator. Click that and it brings up this. It defaults to a 3 by 3, but if you hit the X button over here, you can delete the input and now input any size matrix that you want. Toggling across here gives you different options. Hit the one that looks like a matrix and then pick whatever size you want. So we're going to do a 3 by 3. So let's enter in the 3 by 3 from our notes. Once that's done and you hit enter, it gives you a lot of information about this matrix. Now what we're after are its eigenvalues. Notice the trace and determinant are revealed. The characteristic polynomial is revealed. And so are the eigenvalues and corresponding eigenvectors. So in this case, all the eigenvalues were distinct, -5, 2, and 1. And so we expect exactly one linearly independent eigenvector for each of them. Wolfram is giving us an example of a basis vector. So when we say that v1 is -1, -25, 17, that's a basis vector for the eigenspace corresponding to lambda1, which is -5. Any non-zero multiple of v1 will also work as a basis vector. So you could do +1, +25, -17 as a basis vector instead. Similarly, v2 and v3 are just examples of one possible basis vector for the corresponding eigenspaces. So let's transfer this information to our notes. So we have our 3 eigenvalues. I'll use r's instead of lambdas, but notice that they are all distinct. There are no repeats. They all had multiplicity of 1. And I've written down the 3 corresponding basis vectors for the corresponding eigenspaces. Now these three eigenvectors form a linearly independent set. We can prove this using any of the methods that we've talked about in previous lessons, how to show that a set of vectors forms a linearly independent set. If I construct a matrix out of these vectors and then put that matrix in reduced row echelon form, if you find a pivot position in every column, then it will mean that the vectors that were used to construct the columns of the matrix A are all linearly independent. So here is such a matrix, and if you put it in reduced row echelon form, you will get the following, which has a pivot in every column, so the three columns are in fact linearly independent. Of course, this is also a square matrix, and if a square matrix reduces to the identity matrix, as it does here, then we know that the square matrix is invertible. So all 12 statements regarding square matrices are all true. And also because A is square, we could calculate its determinant to do this instead. And the determinant of this 3 by 3 matrix will be 42, which is not 0, again confirming that the columns of A are linearly independent. We conclude that these eigenvectors are linearly independent. In fact, if you take any eigenvector from the space corresponding to the first eigenvalue, and any eigenvector from the space corresponding to the second eigenvalue, and any eigenvector from the eigenspace corresponding to the third eigenvector, and form a set of three vectors, that set will be linearly independent. So any multiple of this vector combined with any multiple of this vector combined with any multiple of this vector, and I should be saying non-zero multiples, we don't want any zero vectors here, will form a linearly independent set of vectors. Let's look at matrix B. I'll use our Wolfram eigenvalue calculator and input this 4 by 4 matrix. Once you've inputted the matrix correctly and you hit go and scroll down to where I can see the characteristic polynomial, the eigenvalues and eigenvectors. Now notice this only gives us two eigenvalues. This suggests that we have some multiplicities that are more than one in this case. The two distinct eigenvalues are 4 and -1, but what are their multiplicities? That's not clear. You could look at the characteristic polynomial and graph it and use the graph to help determine what the multiplicities are. And in this matrix calculator, if the characteristic polynomial has a hyperlink, you can click it. If you don't see a hyperlink, like I don't see currently, hit the gear symbol over here on the right, and notice a hyperlink becomes available. And when you click it, it takes you to a new page that investigates the properties of this characteristic polynomial, including giving you some graphs. But I'm going to look at the alternate forms that you see right here in the middle, and notice that there's a factored form. So this characteristic polynomial factors into lambda minus 4 times lambda plus 1 cubed. This reveals the multiplicities of the roots. So 4 is one eigenvalue with multiplicity 1, and -1 is an eigenvalue with multiplicity 3. Transferring that information to our notes, we have this information. And then the goal is to find the corresponding eigenspaces. Looking back at the eigenvalue calculator, the eigenvalue lambda 1 equals 4 corresponds to an eigenvector v1 of 4, 15, -10, 5. And because the multiplicity of 4 was 1, this is the only linearly independent eigenvector associated with that eigenvalue. So the eigenspace will be the span of this one eigenvector v1. But the multiplicity of -1 was 3. And from previous discussions, that means that the eigenspace will have at most 3 linearly independent eigenvectors in its basis. But notice only one eigenvector is presented here, v2, which is the vector 1, 0, 0, 0. This is Wolfram alpha communicating to us that this eigenspace, corresponding to -1, only actually has one linearly independent eigenvector in it. We knew it could have up to 3, but in fact in this case there is only one. So let's transfer this information to our notes. Again, summarizing, 4 was an eigenvalue repeated once, multiplicity 1, so we expect exactly one vector to form the basis for the corresponding eigenspace. Now, of course, any non-zero multiple of this vector will also form a basis vector. And the second distinct eigenvalue, -1, could have up to 3 linearly independent eigenvectors to form the basis for its corresponding eigenspace. But it only wound up having 1, as revealed by Wolfram alpha. So only non-zero multiples of this one vector will be eigenvectors corresponding to this eigenvalue -1. If you take any vector from this eigenspace and any vector from this eigenspace, they are going to be linearly independent of each other. In fact, the two basis vectors as they're currently written, you can see clearly that vector v1 is not some multiple of vector v2. And when you only have two vectors and you're trying to determine if they're linearly independent, you just have to establish that they are not multiples of each other. Of course, you could construct a 4x2 matrix and put that 4x2 matrix in reduced row echelon form and see that there are pivots in each column. That will also confirm that the two vectors that form the columns of the matrix are independent. So v1 and v2 are linearly independent. Now, in general, this is going to be true. Note that eigenvectors corresponding to distinct eigenvalues will form linearly independent sets. So take any vector from this eigenspace, and here's a distinct eigenvalue, so take any vector from this eigenspace, and that will form an independent set. And over here, all of the eigenvalues were distinct, so take any vector from this eigenspace, any vector from this eigenspace, and any vector from this eigenspace, and that will form a set of 3 linearly independent vectors. All right, let's go on to the next page. Now we want to explore a little bit more about eigenvalues that repeat. If R is an eigenvalue of A, then non-zero solutions to A minus Ri raised to the P times a vector x equals the 0 vector, where P is more than 1, so this exponent right there could be 2, 3, 4, etc., are called generalized eigenvectors corresponding to eigenvalue R. Note that if P is 1, then such solutions are simply eigenvectors. So if this P is 1, then solving this system means we're just simply finding eigenvectors. Of course, looking for non-zero solutions. But if you square or cube or raise to the 4th this coefficient matrix and then solve the system, you will find non-zero solutions that are called generalized eigenvectors. Now recall that if k is the multiplicity of an eigenvalue r, then the dimension of the corresponding eigenspace is at most k. But now, if k is the multiplicity of an eigenvalue r, then there will exist exactly k linearly independent solutions to, you take the A minus Ri matrix and raise it to the k, raise it to the multiplicity of the eigenvalue, and then solve that system right there, and you will be able, guaranteed, to find exactly k linearly independent generalized eigenvectors. Let's explore these concepts for the matrix below. So this is the same 4x4 matrix we looked at on the previous slide, except I'm calling it A now instead of B. So we had already found the eigenvalues. The eigenvalues were 4 and then -1 with multiplicity 3. So let's explore the first eigenvalue 4. In this case, the k that's referred to up here in our notes is the multiplicity of this eigenvalue, which is 1. To find a basis vector for the corresponding eigenspace, we set up the following. So remove 4 from the main diagonal of A and create this augmented matrix. So here's the result of doing that. The main diagonal, this new main diagonal was achieved from the old main diagonal, except we removed 4 from all entries. So this coefficient matrix right here was found by doing A minus 4i. Now we'll use technology to put this in reduced row echelon form. Identify that we have 3 pivot positions. So we have 1 free variable. 1 free variable implies that there will be 1 linearly independent eigenvector, which is exactly how many we expected because the multiplicity of this eigenvalue is 1. So this is business as usual. But now let's go on to the repeated eigenvalue and see what occurs. So for this eigenvalue, the multiplicity is 3, so k will be 3. And if I remove this eigenvalue from the main diagonal, in other words, calculate A plus I, and then set up an augmented matrix, I get the following. Now let's use technology to put this into reduced row echelon form and see how many free variables we get. Notice that in the reduced row echelon form, we have 1, 2, 3 pivot positions, so we only have 1 free variable, which means that we're only going to get 1 linearly independent eigenvector. This is not surprising, because if we look at the last page, we already knew from Wolfram alpha that this repeated eigenvalue only had 1 eigenvector in the basis of its corresponding eigenspace. So our work here is confirming that knowledge. What we're going to do now is repeat this process, but we're going to do powers of A plus I. Now you can do the power of a plus I by hand, or you can use a matrix calculator to help. But if you do a plus I and square it, you get the 4x4 coefficient matrix we see here, and we augment it with the 0 vector, and then we put this in reduced row echelon form. And notice this time we have only 2 pivot positions. So the first column and the fourth column represent free variables. So we have 2 free variables, which means that we would be able to find 2 linearly independent, and these would not be eigenvectors any longer because we've now done a power of a plus I as opposed to just analyzing a plus I. So we call these generalized eigenvectors. But notice the number of free variables, or the number of linearly independent generalized eigenvectors that we can find in this case, doesn't yet match the multiplicity, which is 3. But if I do this one more time and cube a plus I, and I'll write that a little bit further to the left so I have space to write some more. If we cube a plus I, we get this 4x4 coefficient matrix, and then we augment it with the 0 vector. And now let's put this in reduced row echelon form. Notice we have only 1 pivot position this time. So we have 3 free columns, or 3 free variables. This means that we're going to find 3 linearly independent generalized eigenvectors. Let's go ahead and do that. So let's say our variables are x, y, z, and w. So our general solution will be x. Now x is free, so it's just itself. The pivot position's in the y column, so y is not free. It'll depend on z and w in this case. And the first row would read y minus 4/5 z plus 2/5 w has to be 0. So in other words, y has to be 4/5 of z minus 2/5 of w. Now z is free, so z is itself, and w is free, so w is itself. And here's your general form of the non-zero solutions. Now we're going to decompose this according to free variable. So the free variable x can be multiplied by the following vector, and just grab all the coefficients of x from the 4 components. So we have a coefficient of 1, and then we have no x's, no x's, no x's. Now the next free variable in our list was z, and all the coefficients of z are no z's, 4/5 times z, 1 times z, and 0 z's. And then the final free variable was w. Grab the coefficients of w that you see here, so no w's, negative 2/5 w, no w's, and 1 w. And these 3 vectors that you see here are linearly independent, and they are generalized eigenvectors. Of course, you could do any multiple of them as well. So if you don't like that middle one, that's 0, 4/5, 1, 0, you can multiply it by 5 and write 0, 4, 5, 0 instead. But if you scale any 3 of them, you will still maintain their linear independence. And finally, we were able to find a total number of linearly independent, in this case generalized eigenvectors, so 3 of them, that matched the multiplicity of this eigenvalue, which was also 3. And the theory suggests that this will be guaranteed to happen if you go all the way up to the 3rd power of the matrix a plus I in this case, and then put that matrix in reduced row echelon form, and you'll be guaranteed to have the 3 free variables. Now there are cases where it might actually occur sooner. It's possible that by the time you got to a plus I squared, that there would be 3 free variables. That may occur. But what's guaranteed to happen is that by the time you get to a plus I cubed, you will find 3 free variables matching the multiplicity 3 of this repeated eigenvalue. Now in this course, we won't do any applications of this, but when you take differential equations, these ideas become important as you solve systems of differential equations. Okay, let's go to the next slide. Note that if 0 is an eigenvalue of a, then a minus 0i, which is just a itself, is already singular. This is because when you remove Ri from the matrix A, where R is an eigenvalue, then that result is a singular matrix. This is how we've been finding eigenvalues from the very start. But we also know that the determinant of a matrix is the product of its eigenvalues. So if any one of the eigenvalues is 0, then the product of all the eigenvalues will also be 0, meaning that the determinant of the matrix A will be 0, which will mean that A is a singular matrix. Thus, we can expand once more the equivalence theorem for square matrices. Suppose A is a square matrix with dimensions n by n, then the following statements are all equivalent, meaning they are all either true together or all false together. Furthermore, all the statements apply to A transpose as well. So the first 12 here are the 12 that we've had from the past, but we've added one more at the bottom of the list. So if a matrix is invertible, then 0 is not an eigenvalue of A. But if a matrix is singular or not invertible, then 0 will be at least one eigenvalue of A. So consider the 13 statements above for the matrix below. Now, I'm not going to analyze all 13 statements in light of this matrix, but I do want to connect the 13th statement to some of the others. Let's begin by calculating the determinant of this 2 by 2 matrix. So 1 times negative 4 is negative 4, and then minus, and then 2 times negative 2 is negative 4. So we get negative 4 plus 4, and sure enough, we get 0. So this means that all 13 statements above are false. In particular, it means that this statement here, 13th statement, is false. And so the negation of 0 is not an eigenvalue of A is that 0 is at least one eigenvalue of A. Let's go ahead and find the eigenvalues of this matrix by setting up the characteristic equation. Remove r from the main diagonal, keep the other entries the same, find the determinant. We get 1 minus r times negative 4 minus r, and then minus a negative 4, which will be plus 4. Simplifying this, we wind up getting r squared plus 3r, which factors into r times r plus 3. So sure enough, one of our eigenvalues is 0, and the other one is negative 3. But we get at least 1, 0 eigenvalue, because the matrix A was singular already. All right, let's go to the final page. Now, there isn't much to write on this page. This page serves as a summary of all the concepts from spectral theory. Remember, spectral theory is just the body of theories related to eigenvalues, eigenvectors, and eigenspaces. So here we have a summary of these concepts that we have covered in this course, which constitutes a brief introduction to spectral theory. Now, suppose A is a square matrix with dimensions n by n. Statement 1, the matrix A has n eigenvalues, but they're not necessarily distinct and they're not necessarily real. Now, that's because the characteristic polynomial will be degree n, and algebra theory tells us that a degree n polynomial has n roots, but not necessarily distinct and not necessarily real. Statement 2, the trace of A, which is the sum of the entries on the main diagonal, will also be the sum of the n eigenvalues. So we have two ways to find the trace. Number 3, the determinant of A will be the product of the n eigenvalues. Or you can find the determinant of A using cofactor expansion or other approved methods. Statement 4, the dimension of an eigenspace corresponding to eigenvalue r is at most the multiplicity of r. So if r is repeated 5 times, then the dimension of that eigenspace will be at most 5, meaning that we can find at most 5 linearly independent eigenvectors to form the basis of that eigenspace. Statement 5, eigenvectors corresponding to distinct eigenvalues are linearly independent of each other. We explored that on page 5 of this lecture. Statement 6, 0 is an eigenvalue of A if and only if A is singular. This is what we just recently discussed on the last page. Number 7, if A is symmetric with real entries, then the eigenvalues of A are real. That was discussed on page 2 of this lecture. Number 8, the eigenvalues of a triangular matrix are the entries on the main diagonal. Now, triangular could be upper triangular, lower triangular, or both upper and lower, which just means diagonal. And we explore this idea on page 3. Number 9, if eigenvalues R1 and R2 are non-real complex conjugates, then corresponding eigenvectors V1, V2 are complex conjugates. This was discussed on page 1 of this lecture. And then finally, number 10, if k is more than 1 is the multiplicity of eigenvalue r, then there exist k linearly independent generalized eigenvector solutions to a minus ri raised to the k, so raised to that multiplicity, times vector x equals the 0 vector. And this idea we explored on page 6. So I encourage you, in light of these 10 statements, to go back and look at the several matrices that we explored, both in this lecture and in the previous lecture on eigenspaces. And this concludes our second lesson on eigenspaces.